Thank you very much. So I hope you were around for Ish's and Stefan's talk because mine is basically the third puzzle piece to that. So you need a quantum computer, right? You need fault tolerance. And the thing that most people forget is you actually also need a classical processor to bring that all together. And the problem with classical processors is they are made at three places. One is Taiwan, the other is South Korea, and the third is in the US. And you will notice one thing here is you can't really get the cutting edge nodes here in Germany. Sure, Intel is building a cutting edge node in Magdeburg, but it's still a US headquartered company. And in electronics, you have this huge problem that while we're increasing transistors, things aren't actually looking that rosy. So we had the end of standard scaling around 2006. That's also the time when multi-core processors were introduced. This is where the Intel Core 2 Duo came to life by Intel, and they've been working on multi-core processors ever since, right? Adding more transistors to add more cores. But we are also reaching a bottleneck there. We have the end of Amdahl's law, and Amdahl's law was a law that used to say, okay, if I double my transistor count, my efficiency of the processing will also go up, for example, 2 times. That has slowed down significantly that now while we have billions of transistors on a chip, adding another billion barely makes a dent on performance. And finally, we are reaching the limitations of Moore's law. And I'm not talking specifically about Moore's first law, which everyone always talks about, making transistors smaller. I'm talking about Moore's second law, which what most people don't know is that also the fabrication costs double each generation. So we are talking about 43 billion euros in Magdeburg this year. The next node will cost twice that much. So the question remains, right? If we're hitting so many bottlenecks with electronic computing, is there something else we can do? Is there some better technology to do computing in? And to us, the obvious answer is optical computing. And optical computing isn't actually something new. It's been around for decades. It's been here ever since we can write on paper, ever since we've had lenses in our glasses, right? This is already a form of optical computing. As a matter of fact, also for Neumann, he proposed the optical computer alongside with his electronic computer, but it was just easier to create an electronic one. And right now, the optical computer is still a bit worse than the electronic computer. But the potential is there that it can outscale it easily. We're not saying this is the end-all, be-all technology, but it is the one that will bring us into the next decade. And one thing I also have to stress is talking with customers about this is very difficult. They see optical computing, they think, okay, this is some weird new technology. I'm afraid of it. We've invested so much money in electronics. We've invested 43 billion euros in Magdeburg. Why would I care? So they will never actually propose this to us. So we have to propose it to them. And that's why at Acatonics, we are creating the world's first all-optical computer, right? A system that works using photons and nothing else. We call it an XPU because it's a cross-domain processor, meaning it doesn't only work in the classical domain, we interface it also with quantum computing. And the reason why we do it is because in a high-performance computing environment, in AIs, in data center, you will often find this case. You have extremely high bandwidth capabilities in your interconnects, right? An optical fiber, petabit per second is nothing. But you have no electronics that can saturate that. You are bottlenecked by the speed of your memory, you're bottlenecked by the speed of your compute, and all that leads to the fact that these optical interconnects are never saturated. So you have the slow capacitance effect from electronics, meaning you have low bandwidth. You have electro-optical conversions at each step, moving from domain to domain, which means you have high latencies. And finally, you have all these resistances in your wires, in your processors, which means you have extremely high energy losses, right? We all see that in the heat and cooling requirements of a data center. So we see ourselves as the radicals who propose, okay, let's get rid of the electronics. Why do we even need electronics in a data center? And then we can fully saturate the bandwidth of all optical interconnects. So by having all optical computing, we get rid of all the electro-optical conversions, we get rid of the bandwidth bottlenecks, and we have extremely high switching speeds. We have ultra fast latency because we don't do any conversions. And of course, we don't have or barely any losses because optical waveguides are just so efficient. You might ask, okay, if it's so great, if it's better in everything, why is no one doing it? Well, it's a bit like the car industry, right? Everyone knew, okay, electric cars are possible, you can create electric cars, but the only electric cars we had back in the day were golf carts. And most people thought, okay, this is the pinnacle of an electric car. And the industry bet on hybrid cars, or in our case, on hybrid computing, electro-optical computing. We see that at Intel, we see that at NVIDIA, we see that at other startups, Light Matter, Light Intelligence. They all do this electro-optical computing. The reason they do that is because it's extremely difficult to go all optical, so okay, it seems sensible to do a hybrid approach. And here's a fun quote by Light Matter. It's really hard to do. And finally, people make wrong predictions about all optical computing. They see, oh, it's much larger than electronics, so it has to be difficult to implement. But then again, people thought that about electronics as well, right? A computer with 1,000 vacuum tubes, yeah, sounds a bit very old. And I want to talk about the different types of optical computing. So you have analog optical computing, which is actually the easiest to understand from physics perspective, because if you want to do addition of two numbers, it's basically like adding two different light beams. And if you want to do multiplication, you can think of it as attenuating these light beams, and then you have a multiplication by a number between 0 and 1. And if you combine these two aspects, well, now suddenly you can do matrix vector multiplication, which is already something very vital, for example, for AI. And the cool thing is, you can do all that on a chip. And this is basically what the most basic structure in analog optical computing looks like. It's more or less a Mach-Zehnder interferometer with some extra components. And that's actually what the Light Matter does. So they create these huge networks of Mach-Zehnders to create an electro-optical matrix vector multiplication. And fun fact, it was proposed from two students at MIT, and they both went off to found two different startups, one called Light Intelligence and one called Light Matter. How does it look like in the quantum domain? And now I hope you all remember Stefan's talk, because you've actually seen this circuit before, right? This is the analog optical computing circuit. It's actually very similar to the quantum optical computing circuit. You basically just feed it different data. In the quantum space, it's obviously much, much more difficult to feed because you need either squeeze states or you need single photon sources. So even though these circuits look very similar, they operate completely differently. In the analog domain, you need extremely high precision digital analog converters, extremely high precision analog digital converters. You need an ASIC, an FPGA to program the whole circuit in real time. And of course, ideally, you have it all monolithically integrated. In the quantum domain, as mentioned, you need photon sources, you need squeeze states, you need all these complex devices. If you want to do feed forward, you also need an ASIC, etc. And I want you to look at one thing that's common in both. It's the electronics that's the problem again, right? If the ASIC is a problem, okay, yeah, you won't get there with the coming nodes. So let's now switch over to the idea of replacing an ASIC, replacing an ADC, and all these components using optical ones. How would you do that? You would start with some optical nonlinearity. It actually doesn't matter which one you use, but let's take a very ideal one, where you feed it in some light beam, some intensity, and it responds nonlinear at the end. As a matter of fact, you can use this kind of device to do very simple digital operations. You could, for example, from this device, start with a nonlinear photonic device, create threshold devices. Then from that, you can do discretization. From there, you can go on to optical logic, and then suddenly you have digital processing in the optical domain. Woo, we solved the problem, right? So we have the analog computing guys, we have the quantum computing guys, and with us you have the digital computing guys. And our approach is to combine all these approaches and say, okay, all optical computing, no more electronics. And what we do at Architectronics is we have these two aspects. So on the one hand, of course, we have all the hardware, right, the transistors and all that stuff that go into an all optical digital circuit. But we also have the software to design these chips. And let's take a look at what this future might look like. So here you would have a typical system by a light matter, a light intelligence. It could also be a quantum optical circuit. And the black components are all the electronic parts you would find there. And if we replace that with optical components, suddenly it becomes much more simple, because now you do not need those modulators, you do not need those detectors anymore. You are completely working in the optical domain. Everything is the same latency, everything is the same bandwidth, everything produces the same amount of heat, and the coolest part, everything can be on the same chip. And yeah, now the big question is, okay, we can put it all on the same chip, but can it scale? We all know this graph, right? I showed it earlier. Does that also exist for optics? And yes, as a matter of fact, we are seeing some sort of photonic Moore's law. We're still very early in it. As a matter of fact, we can only integrate as many devices as we could in the 70s in electronics, but we're getting there. And of course, when we look at the speed of electronics, right, the fastest type of electronics can switch in the hundreds of gigahertz range. With photonics, it basically starts there. An optical transistor can switch terahertz. Newest research has shown you can go into the petahertz domain. So where are we at when we think about scaling, right? At the moment, we're integrating maybe 20, maybe 50 devices, but it will continue on. We have already seen now the potential of integrating tens of thousands of transistors in an all-optical circuit. This means we start with our pilot customers, now some simple applications. Then we go into all optical AI and high performance computing, moving towards more and more. And then finally, we get to the point where we can integrate quantum computing and go beyond to have an all optical computing system. Now I want to get back to one point I mentioned in the beginning and in the mid. Right? We were talking about nodes that are not in Europe. And when we think about photonics, we think about old nodes, right? We think about 130 nanometers, 250 nanometers. These are all fabrication technologies which are abundant here in Europe. So if you go towards an all optical computing future, suddenly you can make high performance computing, high performance AI in Europe without having to go to a TSMC. That means you have supply chain security. You have all the available processes here. You don't have to think about, oh, Taiwan is having a war with China. Now you don't have any chips anymore. And Europe is in the lead when it comes to photonics. And these three aspects are actually something which we value the most when it comes to all optical computing, and why we think this is actually the future of computing. And if you want to know more, please come up to me, and would love to talk to you about the optical revolution. Thank you very much.
Thank you very much, Michael. So what are your questions for Michael?
Hi, thanks for the nice talk. I was wondering also if, like for normal computers, cooling is required. Is cooling something that is an issue for this type of systems? And are we talking about cooling in the room temperature level, or is there even an advantage of lowering the noise for, let's say, the quantum photonic approach?
Yeah, that's the really cool part. all of this is room temperature. Even the quantum computing side would be room temperature, because we would be basing this off measurement-based quantum computing, and normally there you have the cooling in the detectors, right? And since we don't need those, we would be doing it all optically using amplifiers, and these work in room temperature. So, yeah. Cooling has a different type of issue for us, is that we actually pump heat into the system. For us, not a lot, but we actually have to cool that away, but not sub-Kelvin cooling. Yeah. Exactly, normal PC cooling.
We have another question.
Thank you for the nice presentation. What is the biggest bottleneck? It sounds way too good.
Okay, I've been talking about computing. One thing I didn't mention is memory. And optical memory, while it is super fast, in theory it's the best type of memory you can have. There's a weird disconnect that we can do extremely high density read-only memory, and we can do extremely fast memory. But in between, we have this lag where, let's call it random access memory, is actually very difficult to do all optically. We have a solution for that, but yeah, scaling that up will be an issue. So we can do terabytes of read-only memory, or we can do very low volume, high-speed memory. But yeah, the mid-range is difficult.
Do we have one more question? All right. Thank you very much, Michael.